Okay, so we've managed to successfully develop expressions for our mass matrix, our element boundary flux, and our stiffness matrix, and so we can put this together into a very compact form for our semi-discrete system. We call it a semi-discrete system because while we've handled the spatial discretization, we still have a time derivative of our solution coefficients. So for any particular time step, we do have our solution coefficients, and this starts from some initial solution coefficients. We'd like to calculate the time rate of change of our coefficients so that we can use that in our time discretization. So in other words, if we have imagine this is one of the solution coefficients. At any point in time, we have a value here, right? So this is, call it A. And if we have some idea of the rate of change of A, then we can step some distance, call it t prime, into the future. And if we know the rate of change of our solution and we have the actual value, we can make some prediction about what the future value will be. But in order to do this, we need to isolate the time derivative of our coefficients. So to do this, we add our stiffness, we subtract our element boundary flux, and then we're left with this term here on the one side. So we'll need to invert this mass matrix, multiply by the inverse of the mass matrix, so it cancels out on this side and comes over on this side. So notice in the act of multiplying by the inverse of the mass matrix, we're sort of implicitly solving a linear system. In this case, it's a relatively small linear system. We just have two unknowns, but because they're added together, because the mass matrix is full, we are essentially implicitly solving a small linear system. So let's see what we can then do with our time discretization. So we'll use a very simple forward Euler approach. So the forward Euler is what's called an explicit method. So in other words, we have our value at a particular time, and we just simply march forward in time boldly using our known rate of change of our solution approximation. You could imagine that instead you would try to predict a future value, and then based on your calculated rate of change, you would try to reconcile such that your predicted future matches your current situation. This would be called what's called a backward Euler approach. So we need to discretize in time our semi-discrete system, and the forward Euler approach is very, very simple. As you might be suggested by this simple drawing, the geometry of the problem is such that our predicted future time here, so this is called t plus 1, our solution values are just simply the current solution values plus the rate of change of our solution values times some small time step here, delta t. And notice that unless we need to do something in post-processing, we don't need to keep the previous time steps coefficients. We can just simply overwrite them, and this helps to save memory. We may want to, every so often, save our solution values so that we can reconstruct the time dynamic behavior of our overall system, but typically you don't need to save your solution coefficients every single time step. Typically your time steps are, especially in an explicit method, are much shorter than anything interesting going on in the system. But it's important to think about how we choose delta t. Could we have delta t be arbitrarily large? So imagine we have some sort of, river flowing, and we have maybe a beach ball being carried around on that river. Clearly, if we look a millisecond into the future, any predictions you make are probably going to be pretty good. But now imagine that instead of looking a millisecond to the future, we look 10 seconds to the future. But we assume that the beach ball is doing the same thing it's doing that whole entire 10 seconds. That might give us problems because there's no guarantee that what we are observing the beach ball doing currently is what it'll do for any arbitrary length of time. So how do you think we can potentially relate this to quantitatively to our discretization of our system? Well, we'll have to defer this question to the demonstration of the linear 1D solver so that we can investigate and see how big can we potentially make this time step before we encounter problems, and can we determine what the largest time step we can make safely is.